Hi students, already we discussed a basic concept of electrostatic forces. There we studied about the properties, charge, types of charges, method of charging, and next we studied about Coulomb's law, vector form of Coulomb's law, and today we want to explain the concept of electric field. So what will be the electric field? So here initially we will consider a source charge. Initially we consider a source charge denotes with capital Q. Source charge denotes with capital Q, and we are considering this source charge as a positive charge. Positive charge. So whenever we consider this source charge due to a natural force, it will be radiates energy. So radiates energy in all directions. But here we consider it is a uniform, like a scale. So it will radiates energy in a straight line. That's we call as a uniform field lines. And we will discuss the field lines concept after the electric field. So how the field lines will be works. So we consider uniform speed lines. Next we will consider one text charge. We will consider one text charge which denotes with small q naught, and this charge will be a positive charge. Here also whenever we have a natural force, it will be radiates in all directions. Radiates in all directions. So to define the electric field, here we consider the two terms. One will be the source charge which has a high strength, and other we have a text charge which has a small charge. So whenever we are placing this text charge in a source charge, automatically the source charge will be negligible. So to define this we will define electric field. So electric field is nothing but, so we will define electric field is an EF. So electric field is a region around a charge in which another charge experience force when brought out. So when brought out. Okay. So initially we consider a source charge. It was radiating some field lines. So that's whenever we consider a field in a region around a charge. So around a charge it will radiates in all directions. Here we consider one text charge. So text charge means here we have an intensity. Electric field intensity. It denotes with E. So E is nothing but, we can define this, E is nothing but ratio between force upon text charge. So whatever the text charge we consider, and unit will be force units will be a Newton and charge unit will be a Coulomb. So this will be the unit. Okay. Now here we have a source charge and we have a text charge. Whenever we have a text charge or source charge, it generates some force with respect to the charge. That's ratio of force upon either text charge, a ratio upon force upon a source charge whenever we have a point. So whenever we have a point, this is we call electric field due to a point charge. So whenever we consider single point. Now we are bringing this charge, whatever the text charge we consider, we are bringing this charge towards the field. Then the charge also experiences the same force. That's a reason around the charge in which another charge experiences a force when it's brought out. So now we are bringing this charge. So whatever the text charge, we are bringing it to here. This will be a text charge. And suppose we place it, this text charge at distance of r. Okay. Now according to, already we stated a Coulomb's law. So according to Coulomb's law, what is the Coulomb's law? The charge is directly proportional to that. So force is directly proportional to product of their charges and inversely proportional to square of its distance. That force is equals to K into capital Q small q naught divided by the distance as a square. This we represented as an equation 1. And according to field intensity, we have a E is equals to force upon charge. So based upon this, we get force is equals to field into Q naught. This we consider as a equation 2. Now substituting equation 2 in equation 1. So we are substituting the value E Q naught is equals to K Q naught divided by R square. So where Q naught will be cancelled. So we get the value E is equals to K Q by R square. This will be the electric field, so due to a point charge. So already we defined, so whenever a source charge, it has a high strength and the text charge, it has a small strength. So whenever we are placing a test charge in a source charge, automatically the source charge will be negligible. At the end of the expression, we won't get the expression of text. So it will be negligible due to the strength of the main, that's a source charge. If you want to define the units, already we defined it's a Newton per Coulomb according to field intensity. But according to this expression, what will be the unit? So already we know the value of K. So K is nothing but permittivity of free space. The unit of free space will be, so unit of K. So what is the unit of K? Already we discussed, it will be a Newton meter square per Coulomb square. Okay, we are substituting those values. So K, we have a value, charge we have a Coulomb, and distance will be a meter square. By substituting those values, E unit will be K Newton meter square per Coulomb square into, what is the units of charge? It will be a Coulomb divided by the distance will be a meter square. So Coulomb meter square will be cancelled, Coulomb will be cancelled. Again we will get Newton per Coulomb. This will be the unit of electric field. But further, if you consider, we can write this also as volt per meter. So volt per meter. So how you got this means we have to know about a potential gradient. So it will be discussed in a further concept, but whenever we are defining the electric field due to a point charge, initially we consider a source charge and we are considering a text charge. Now whenever there is a field, so electric field is a region around a charge in which another charge experiences a force when we brought out. So whenever we are placing the test charge, if you place it in a source charge, then source charge also will experience the same force. But according to the basic definitions, electric field intensity, which denotes E for a point charge, for a particular point charge, electric field is equals to ratio of force upon charge, and unit will be a force unit Newton and charge unit Coulomb. And based upon this we get the value of force. Force is equals to E into cross multiplication of Q naught. According to Coulomb's law, so we place the text charge in the field, so it has a certain distance of r. According to Coulomb's law, whenever we have a two charges with certain distance, automatically it applicable Coulomb's law. That's a force is equals to K Q naught by r square. It represents as an equation 1, and already we have a equation 2. Substituting equation 2 in equation 1, we get the value of E is equals to KQ by r square. And if you want to define the units of electric field based on this equation, means already we know K is equals to Newton meter square per Coulomb square. Already discussed in the previous lecture. We substituted the value of K, and Q is equals to Coulombs, and distance square will be a meter square. Again we will get the same unit of electric field intensity. This is a concept of electric field. Suppose if you want to represent in vector form, which electric field only represents the magnitude. If you want to represent in vector form, so vector form means E direction is equals to KQ by r square along the direction of r. So whatever the r, so we consider along the direction of r. Already we know about unit vector. So unit vector, what's the definition of unit vector? Suppose if you have a cap, along the direction, A cap is equals to A direction by A modulus. In the same way, electric field we get E is equals to KQ by r square into r direction by modulus of r. So we get E is equals to KQ r direction by rq. It is in vector form. So next, now we discuss electric field due to point charge for a single source. Now we will define electric field due to multiple charges. So multiple charges means, suppose here we have a charge Q1, charge Q2, charge Q3. So we have three charges. Suppose here we somewhere we consider a point charge, we represent with P, it's a positive. Here also we consider positive, positive, positive. Okay. Now we are considering the three charges Q1, Q2, Q3 are placed at a distances of R1P, R2P, R3P. So not only three charges, if you place a n number of charges also it's applicable. So we are considering Q1, Q2, Q3, so on up to Qn are placed at the distance of R1P, R2P, R3P, so on up to Rnp. So we consider point charge. So we consider the distances from Q1 to P. It has a R1P, Q2 to P, it will be a R2P, and Q2 3P, R3P. So whenever we are considering a point charge, the point charge will experience a field. That's an electric field with E1. So charge 1 will experience a force of E1. Similarly, charge 2 will experience the force of E2. Charge 3 will experience the force of Q3 with respect to a point charge P. Okay, we will define. If you consider general electric field due to point charge P, so what will be the force experience? E is equals to K Q by R square. Okay, so whenever we consider point charge, but here we have a multiple charges. For multiple charges means, so every point we have a experiences of electric field. So here we have electric field 1. So what will be the electric field 1? K into, instead of Q we will represent this as a Q1 divided by R1. The distance will be R1P square. Similarly for E2, K Q2 by R2P square. Similarly for third one, electric field experience due to a point charge, this will be a K Q3 by R3P square. We need a value of net electric field. So what will be the net electric field means all the three we combine. That's a electric field. Net electric field is equals to combination of E1 plus E2 plus E3. If you consider n number of charges, we will consider as a n. So here we will consider n number of charges, suppose. So we have up to n. So what will be the n charge here? So En is equals to K Qn divided by Rn P square. Substitute all those values. By substituting all those values, we get K Q1 divided by R1 P square plus K Q2 divided by R2 P square plus K Q3 divided by R3 P square plus so on up to plus K Qn divided by Rn P square. So we substituted all the values, so we get the value of electric field. So here if you consider K will be a constant, K into Q1 divided by R1 P square plus Q2 divided by R2 P square plus Q3 divided by R3 P square plus so on up to Qn divided by Rn P square. If you substitute in Sigbat format, that's K value we know 1 by 4 pi epsilon naught. Since the value of K already we discussed 1 by 4 pi epsilon naught for theoretically, and if you substitute the values we get 9 into 10 to the power of 9. So we are writing theoretically, so 1 by 4 pi epsilon naught, we are taking Sigmat format. Sigmat here 1, 2, 3 so on up to n. That's a I stands from 1 to n. So Q of I divided by R of I P. R of I P whole square. This is the electric field for a multiple charges. Suppose if you want to represent in vector form. So vector form means, so we have to mention the direction KQ by R square along with R cap. In the same way, here also we will represent E is equals to 1 by 4 pi epsilon naught. Sigma tends from I tends to 1 to n Q of I divided by R I P square into R I P cap. This will be the vector form. And already we know about vector. So R cap, we can represent this as a R direction by modulus of R. Similarly, if it is a R I P cap, means we will write R I P direction by R I P modulus. So next one, electric field lines. So electric field lines means it is a line drawn in such a way that is tangent to it at any point. Tangent to it at any point gives the direction of electric field at that point. So maybe it was not clear, but we will represent in diagrammatically. So generally we have two types of charges. So one will be a positive charge, other will be a negative charge. Here first we will go for point charges. So point charges means we have only a single charge. Single charge means we will consider either positive charge or negative charge. First we will represent single charge as a positive charge. Here we have only a single charge. Similarly, we have a second one. This we have a first one, and this will be the second one, which has a negative charge. So already in the types of charges in the first lecture, types of charges. So types of charges are classified into two types, positive charge and negative charge. Positive charge means whenever, simply we call this as a donates. So donate means whatever the charge we have, it will be donates to the another charge. So whenever, according to field lines, whenever we have a point, it will be radiate charge in all directions. So depending upon the strength of the charge, the field lines will be depends. For example, if you consider like your electric bulbs, suppose we have a 1 volt bulb, so the radiation will be a small. Whenever we consider 10 volts, the radiation will be a little more. Whenever we consider 100 volts bulb, the intensity will be a more. Similarly, here we have a positive charge, it will be radiates. Similarly, if you have a negative charge, it's also radiates in all directions. Okay. Now, according to a positive charge is nothing but donates. It wants to lose some electrons. So already we call positive is nothing but losing of electrons. Similarly, if you consider a negative charge means donates ki opposite. So donates means acceptor. So it's called gaining of electrons. So gaining means it was taking inside. So we will consider the directions. So positive charge is nothing but it's a positive charge. It's a losing of electrons. Losing of electrons means we are leaving some charge which will comes outward. So which will comes in outward direction. Okay. So donates. Positive charge means the direction will be in outward. So whenever we are giving a negative charge, gaining of electron, which we call as an acceptor. Acceptor means which will comes inside. The field lines will be a inside. That's your direction will be inward. So whenever we consider a positive charge, we call this as a losing of electrons, and negative charge is called gaining of electrons. So losing means it was donating some electrons. Negative gaining means it was accepting some electrons. So whenever we have a positive charge or negative charge individually, that's a single charges, point charges, it will radiate energy. But whenever we consider a positive, then it will donate. It means it was coming outward direction. If you consider negative charge, it will be accepts. It will becomes inward direction. So we completed the first one, point charge. In that we have a two types. Now we will define two charges. So two charges at a time. Two charges at a time means, so either we will consider positive positive, or positive negative, or negative negative. We have three options. Either we will consider positive positive, negative negative, or positive negative. So already we know. So positive positive means it will be in repulsion. It's also in repulsion. It will be in attraction. So based upon this we will represent three diagrams. The first one, whenever we consider positive charge, if you place the one more positive charge at certain distance r, the positive charge will be repelled. So will be repelled means whenever it was sending some rays, it's also sending some field lines. Both the field lines will not be intersect because both are in repulsion. So object will be, direction of a field lines will be moves like this. So whenever we are placing at certain distance. And what will be the direction? The positive always donates. The arrow will be in outward direction. So both are in outward direction. That's we have a repulsion. That's when we have a third one. Two positive charges are placed at the distance, at some distance, and both will be repelled. So this will be a representation of field lines. Suppose if you consider both are of negative charges. So both are of negative charges. If you place it at the distance some r, then negative negative also repels, and we get the same field lines. Same representation of field lines, but no will attract. And what is the direction of field lines? The field lines will be inward. So both having inward direction. So both will be in inward direction. But whenever we consider one is a positive, this is a fourth case. So what's the fourth case? When two charges are of negative charges. And here also we get repulsion. But at last we have one will be a positive charge, this will be a fifth case. One will be a positive charge, other will be a negative charge. So whenever we are placing two charges at some distance, so both will be attract. So both will be attract means this is the field lines. The positive attracts negative, positive attracts negative, positive attracts negative. So these are the field lines we get. Now what will be the direction? Here we have a two direction. Positive means it will be a outward direction. So all we have a outward direction. But when coming to the negative, so negative means it will be a inward direction. The data will be inward. So we represented 5 blocks. So if you have a more strength, suppose in the fifth example, we consider positive charge and negative charge. Suppose here we have a positive is more. Suppose in this example consider positive as a 4 coulombs of charge. 4 microcoulombs of charge. Here we have a minus 2 microcoulombs of charge. So 4 has a high strength. So field lines will be a more here. The field lines will be a more when compared to the second one. These are about field lines. So field lines means whenever we consider positive charge, it will be radiated outward direction. Whenever we consider a point charge of negative, it will be an inward direction. And next two charges we consider. Positive means there is a repulsion. So there is a no attraction. And negative means there is a repulsion. There is a no attraction. And if you consider last one, we have a both positive and negative charges. So positive and negative charges means one will be moves in outward direction, other will be moves in a inward direction. And whenever we represent the field lines is always tangential. Always tangential means, so if you consider a point charge positive, it's always 90 degrees with respect to that point. That will be a 90 degrees which will move in all directions. Next, we have defined some electric field lines. Now we will define the properties of field lines. Here we have some properties of field lines. The first one, the field line starts from positive charge and ends at negative charge. So whenever we consider the field lines, he mentioned the direction. It's always starts from positive. Starts from positive, ends at negative. The first one. The field lines, whenever we represented the field lines, electric field lines always starts from positive and set negative. So whenever we have a two charges, but whenever we have a point charge, so whenever we have a point charge, either positive charge or negative charge, it will be moves in a, it will be a starts or ends. Because we have a direction. Whenever it was start means it was moving in an outward direction. Whenever it was end means it will be moves in this direction. And first point, it's always starts from positive and set negative. And whenever we consider the point charges, that's the single charges, it's always starts ends at infinity. At infinity. It's the first point. Second point, in a charge-free region, electric field lines cannot be taken to be a continuous curve without any breaks. For example, if you consider a wire. For example, if you consider a wire, here we have a switchboard. Here we have a on-off switch. And other side, we consider a bulb. Other side we consider a bulb, and from switch to bulb, so we have a continuous wire. Suppose if you break here, and we switch on, whenever we switch on, the field lines will passes through the point till we have a break. So whenever we have a break, it won't jump the electrons. It will be break here. So bulb won't glow. So bulb won't glow. That's a point. In a charge-free region, electric field lines can be taken to be a continuous curves without any breaks. Whenever we have a break, automatically field lines won't exist. And where the starting point to break point, it will be an end point. Suppose if you have one more break here. If you have one more break here. So already it was breaking at the first end only. It won't go till the second point. It won't flow to the second point. So we need a continuous. So if you want to glow the bulb, so from switchboard to bulb, we need a continuous wire. And third point, the two field lines cannot be intersect each other. So for example, if you consider here we have a one positive charge. Positive charge means it will be radiated in unidirection. That will be a tangential. So it has only a particular direction. It was moving in outward direction. If you consider negative, it will be a inward direction. Okay, but no two field lines. The two field lines can never come each other. If they did, the field at that point of intersection will not have a unique direction. So already we stated a field lines always starts from positive or ends at negative. Whenever we consider the positive charge, a single point charge, it will be starts ends at infinity. Similarly, if you consider negative charge, it starts from infinity, ends at the point. Okay, so we have a unidirection. So generally, whenever we consider, this won't change its direction. Like whenever there is an intersection, these type of charge won't exist. So there is a no intersection. Suppose if there is an intersection means they may have a chance of another charge at that point. I hope you're clear. So whenever we consider a point charge, it has a unique direction. It will move in a particular direction that will be a tangential to the surface. But whenever we have a cross section, if one signal touches another signal like this type of charge won't exist. So whenever this is a direction, the other will be a tangential to this. They won't intersect each other. And fourth point, the electric field lines does not form any closed loop. So any closed loop means, for example, if you consider we have a positive charge, negative charge. According to the first point, it's always starts from positive. Starts from positive and it will be ends at negative. So there is a no field lines which starts from negative ends at positive. So whenever we consider this will like a closed loop. This type of field lines also won't exist. So here we have a clear-cut concept of field lines. So whenever we are good in these four properties, okay, the first one, the field lines always starts from positive and set negative. So there is a no signal which starts from negative and set positive. If it is dead means this the circuit will be a wrong. And second, whenever we consider the field lines, it will be a continuous form without having any breaks. If you have any breaks means that type of field lines also won't exist. Two field lines never cross each other. Never cross each other. If they cross means that type of field lines also won't exist. And field lines does not form any closed loop. So it's always starts from positive and set negative. So we don't have a chance of negative to positive. And suppose if you have your NCERT textbooks, there we have some examples. Try to solve those examples. They represent around 4 to 5 field lines and ask which one is a right. So depending upon the directions, you may clear that. And try the question. And next concept, electric flux. So next concept, electric flux. In these videos, I am giving only a theoretical part. At the end of this section, it means at the end of this chapter. So we will make one video. We will define all the numericals. We will do all the numericals based upon topic wise. So already we defined charge, types of charges, method of charging. Next we have a different terms for every definition. So till now we are doing only a theoretical part, and we will do the last video. At that we will give roughly a 20 or 15 numericals based on all these topics. This is clear. So we have a concept of electric flux. So electric flux means the number of field lines passes through a given surface area, which is denotes with phi. That's a number of field lines passes through the given surface area. So we will discuss the formula, and it denotes with phi. Okay. So generally, to define the flux, initially we will consider one source charge. That we have a positive charge. We consider uniform field lines. So here we have a positive charge means all we are moving. That's it starts from positive and set negative. All are having equidistance. It means this will be a so we represented only a field lines. According to a field line concept, the field line starts from positive and ends at negative. Okay, so here we started from positive, we ended with negative. Now we want to define the flux. A flux is nothing but number of field lines passes through the given surface area. Suppose we place the one obstacle here. We place the one block. Suppose these are the directions. One second. Suppose, consider an example. We started a field lines. So one end we consider this will be a positive, that's a source charge, and from there we are representing some field lines. Whenever we are placing one obstacle, so whenever we are placing obstacle, the output will become a 0. There is a no field lines will be comes out. There will be a no field lines will be comes out because there is a no specific area. Okay, so whenever we represented a positive field lines, here we are placing a one substance. So due to substance, there we have a obstacle. So obstacle means all positive charges at the other side. It will be a mouse. But at the surface, at that substance, the output is 0. So there is a no field lines will be passes through that block. Okay. What is the direction of field lines? It's always the direction of electric field lines. It's always starts from positive and set negative. So here we have a field lines. This is the direction of field lines. Okay. So whatever the substance we consider, suppose if I place the small hole here with what particular area. So we define at particular area we place the some hole at the substance. Whenever we place the hole, automatically from that hole the field lines will comes out. And this is the direction of area. Okay. The electric flux is nothing but number of field lines passes through the given surface area denotes with phi. Now what will be the definition? Flux is equals to electric field direction and area direction. and this will be equals to, flux is equals to EA, that's a dot product, two vectors, dot product into cos theta. So already we studied about vector. And the electric flux, what type of quantity it was? The product of two vectors, where E has a direction and area as a direction. Both are having a direction. The product of two vectors will give us a scalar. The product of two vectors will give us a scalar. So flux will be a scalar quantity. Okay, so this is a definition. So EA, so formula for flux. Okay, suppose if you consider here, second example, the same, if you consider same source charge with positive strength, it was radiating some field lines. Now we will place substance in this order. In this order means all the field lines will come through this point, and whenever we are placing a small hole area, the area direction will be in upward direction, and this is the direction of electric field. In the first concept, whatever the substance we consider, so these are the field lines, so these are the field lines which was passes, and substance we consider which is perpendicular substance, clear, so just make it clear, these are the field lines which passes in a straight line, it starts from positive and set negative. Suppose if you place the one substance here, the substance is always perpendicular to the field lines. The output will become a zero because there is a no area. The area is zero. Now, if you place the area at this point, whatever the field lines it was passes, we get the output at this point. We will get the output at this point. So, here the field lines, area, both are in same direction. In the first example, field lines, substance, both are perpendicular. Field lines, area, both will be in same direction. I hope you're clear. In the second example, again we consider field lines. Again we consider field lines. Now we are placing a substance parallel to the field lines. And the area we place, it will becomes at the top point. Now, field lines, substance, both are parallel, and whatever the substance, that's the area we consider, it will be a perpendicular. I hope it was clear. So in the first example, whatever the field lines and area both are in same direction, so that we get the field lines. If you consider second example, whatever the field lines all are in this direction, and whatever the area, it was moving in upward direction. So in first example, area, that's a electric field and area, so both are parallel. Both are parallel. Parallel means what will be the angle? Theta will be equals to 0. In second example, field lines and area both are perpendicular. So perpendicular means angle will be a 90 degrees. I hope it was clear. So we will make a relation between number of field lines and area. We are not considering the substance. Now the question is when the flux will be a maximum, when the flux will be a minimum. So substitute those values. Already we know the formula of flux is equals to EA cos theta. Suppose if you place the theta, if theta is equals to 0, which implies flux is equals to EA cos 0. Cos 0 is equals to 1. We get the number of field lines out. If theta is equals to 90 degrees, then flux is equals to EA cos 90. Cos 90 is equals to 0, the output will become a 0. So when theta is equals to 0, then it will be a maximum and this will be a minimum. I hope it was clear. Again, I want to explain. I want to repeat the concept. Electric flux is nothing but a number of field lines passes through the given surface area, and it denotes with flux phi. Initially, we considered the field lines. It was radiating a field lines in all direction, and we are considering it was a uniform straight line. And we placed the one substance. So this is the direction of field lines. We placed the substance. Whenever we place the substance, the output will become a 0. There is a no field lines at the end, because the substance will be an obstacle here. Now we are placing a small hole here. Whenever we are placing a hole, at that hole the field lines will be pass out. So field lines and area both are in parallel. The angle will be a 0 degrees. If you consider second example, here we have a field lines. The substance we consider in this direction, the area will be in upward. The value will be a 90 degrees. So based upon this, we represent the flux. So when will be the flux maximum and when will be the flux minimum means, according to your two representation, when field lines and area both are in same direction, then flux will be a maximum. If field lines and area both are perpendicular, then it will be a minimum. So question, when it will be a maximum and when it will be a minimum? If electric field lines and area both having same direction, it means angle will be a 0. Angle will be a 0. So according to formula, flux is equals to EA cos 0. So cos 0 is equals to 1. So we get the EA. Then flux will be a maximum. Suppose if E and A both are perpendicular to each other. Perpendicular to each other means theta value will become a 90 degrees. Then flux is equals to EA cos 90. Cos 90 is equals to 0. The flux will be a minimum. So when will be a maximum, when will be a minimum means, if E and A both are having same direction, then theta will be equals to 0. According to definition, flux is equal to EA cos theta. The flux EA cos theta value is 0. Cos 0 is equals to 1. Then the flux will be a maximum. In the second one, if E and A both are perpendicular to each other, the field lines and area both are perpendicular to each other means the angle made by them is 90 degrees. Then according to a formula, cos theta is equals to, the flux is equals to EA cos 90. Cos 90 is equals to 0. The flux will be a minimum. I hope it was clear. In the next concept, we will discuss about the dipole, axial dipole, equatorial dipole, and Gauss theorem. And Gauss theorem is very important concept. So it will take 2 more videos. And after that, we will go for numericals for each and every definition and each and every derivation. I hope today concept is clear. Maybe you have a doubt in flux, but it will be clear in the Gauss concept, because using the Gauss concept, flux concept, we will derive the Gauss. So at the end of all videos, I hope electrostatic force will be clear to you all. Thank you.